All right. Thanks everybody for joining today. Uh, we have a little bit of a change of pace. We've had a couple of networking talks a couple weeks in a row, and didn't want to forget that. Yeah, we do other stuff besides networking on these talks. So Garhan was kind enough to volunteer, and this is actually something I'm really interested in hearing about because I know that this has been a work in progress for a little bit. He's going to be talking about a full stack view of an analysis facility. And when I saw all those letters crammed together there, it made my head hurt a little bit. So I'm hoping that he will disambiguate that a little bit and give us a little bit of an overview of the work that they're doing down at Nebraska Lincoln. So I'll turn it over to you.
All right, thank you. So yes, I'm Garhan Attebury. I'm with the University of Nebraska Lincoln with our Holland Computing Center. We do the research computing. I've also got a lot of ties with the high energy physics community, especially USCMS, as we're one of the tier 2 sites for that. And I've got my hands in a lot of things, NSF, cyber infrastructure, research platforms, those types of things. So I enjoy this. Yes, the acronym there, it's not actually an acronym. I typed the letters out to see what it looked like. Kind of looks like it could be a function call, I guess, or maybe a really bad file system name. If anybody wants to steal that and make a new file system, feel free to. But we'll go ahead and get started. So the full stack view, full stack means different things to different people. For me, in this case, I'm going to try to, generalize things and not deep dive into any particular technology. And maybe ironically, I'm going to end with networking stuff because the networking stuff is what I like the most, I suppose, out of all this, or at least what I can wrap my head around the best. So while this goes away from your networking talks, we'll go right back to networking talks at the end. So I will try to describe, the particular problem that this analysis facility is trying to solve. It's, we're kind of high energy physics heavy here since that's the realm that I work in and what this particular project is in, but I think a lot of these ideas can be applied elsewhere. If it wasn't, I think it was in the abstract, Kubernetes is certainly involved. Whether you like that or not, everybody has their own opinions. I have my own hatred of it at times. And all of the fast moving varying technologies that go along. So yes, there will be a bunch of cloud native buzzwords. There are so many buzzwords. There's a giant picture of them at one point. We did build a thing, so this kind of analysis facility actually exists. In fact, I believe I mentioned a football stadium in the abstract, and so yes, indeed, that little circle there in the picture is roughly where all of this stuff lives. We have a data center underneath the south end of the football stadium here in Nebraska. I'll touch on networking as I said, how the bits get from a user somewhere in the world to all of this stuff that got plumbed together. And then brief comments on operations, if this was a good idea, was it successful, or is it? It's very, very much an ongoing process still. But we'll kind of dive in with the problem, I guess. I think it can be summarized as, the problem arises when researcher expectations and what they need diverges from whatever computing is currently providing. This, happens. There's an ebb and flow of research computing. Sometimes things are great, and then sometimes it just doesn't fit. So, in the olden days, maybe not, when dinosaurs roamed, but we had traditional batch computing, high throughput computing. And I said reign supreme because it's very much still true, especially in the physics community. There's a whole slew of global scale computing that has been built up over the years. Tier 0 at CERN, national labs is tier 1s, tier 2s at various academic universities like us, tier 3s at other institutions, all of which typically have batch computing, and that's how you get your actual problem solved. That's not necessarily a bad thing, but sometimes that form of computing just doesn't fit what researchers need. I used to give tours. I don't anymore because we have somebody else that does that a lot now. And I would always, or oftentimes, use an analogy of a user, physicist or physics grad student or something, sitting at a coffee shop in Italy. I don't know why it had to be Italy. That makes sense, I guess. With their laptop, and they could submit, a workflow, and it could come and run on our hardware that was in the data center below me, where we had a window, and that's where I was giving the tour at. And certainly, it seemed cool and kind of novel at the time. This was 10 plus years ago, maybe. And it is still neat in some sense that happens. But of course, nowadays, everybody expects always-on computing. You expect to use the word, everything's in the cloud. It's always just there. The idea of submitting jobs that you have to wait because they go somewhere else. You maybe have to copy your files back. Not a very interactive process. And, that used to be cool because it was what we had. And now it's kind of like, yeah, maybe not the best. And so, we have a need, has arisen to do things a little bit differently. At the same time here, we have a lot of new tools in the last, decade or so. Kubernetes is still fairly new. All sorts of various things have popped up around that and the ideas of cloud native tools. And there's also new science tools out there, a lot of work in Python. A lot of times people thought Python was slow and you didn't do science that way, but the amount of big data frameworks that have cropped up and what people can do is always evolving and very rapidly. And so we have a shift now that we have the ability to do things in a different way than this batch computing. And like I said, people typically, want instant gratification with computers. Maybe that's always been true, but now it certainly is still true. So maybe interactivity, in your research with computers is more desirable. So I'm going to dig myself a hole and start with the stuff that I know the least about. And hopefully by the end of this, I'll have dug out of the hole and, we'll get back to the networking or the end of the talk, I guess. So the thing I know the least about is physics, probably. I'm not an actual physicist. I just work with a bunch of them and they pay me somehow. So my naive view of what physicists do with computers is they have a lot of root files, that's the file format, and lots and lots of data, probably one of the largest in volume of data for science domains. And they loop over that data, looking at events, calculating things, and it's really expensive. Expensive IO-wise, expensive volume-wise, transferring data around. And it's, that's all good and wonderful. And they certainly can use computers, whatever computers you can give them. So the traditional kind of way of doing this, it was or is referred to as kind of row-wise analysis, where you are, doing a serial processing of event data. It's loops over whatever data you have. And like I said, it's really intensive. Right now, 2022 is smack dab in the middle of this analysis grand challenge that's going on in the high energy physics community. And that challenge is really to look at how this can be improved and rethink the data pipelines, rethink the tools that people have made in order to essentially get more work done. One of the ways that you can do that is to move or change the way you're analyzing your data, and in particular, one way that I say we're, but one way that is being done in the group I'm with and with this type of physics is to do columnar data. And I'm not a science. I'm neither a physicist nor a computer scientist really at this point. But essentially you're reorganizing the data and altering it or extracting the bits and pieces you need in such a way that you can make use of these new data pipelines and data frameworks that exist to essentially go faster. I was thinking, the last time I dug into any kind of, what was going on in computer science and data analysis, and it had been quite a while. There's a lot of new terms and new tools out there that I hadn't heard of before. Awkward arrays, jagged arrays, there's a lot of new work in this area on analyzing data faster and organizing data in better ways. And as I said too, there's a lot of new tools out there. Python especially is still very, very, very popular. There are a lot of tools that have come up based on Python. We'll talk about a few of them. Those are getting more and more common. And as I said, this analysis challenge was to use those tools and figure out how do we make all this go faster. And the need exists. There's, I don't remember the timeline, 2027, I think, maybe it got pushed back. There's a high luminosity change to the LHC. So essentially all of the stuff that's currently being generated by high energy physics, it gets generated faster and in a larger volumes. Maybe, I don't know if it's an order of magnitude precisely, but something in that area. So the need to not waste time computing in the old ways is there. So I'm going to jump in and talk about one of the tools. Dask was on that previous list. Dask itself is a parallel computing library. So essentially a way to framework by which you can parallelize whatever science you are doing. It is gained a lot of popularity lately. It supports a lot of popular Python tools, NumPy, pandas, big data or pandas data frames, all of these things that are very common in the data analytic ecosystem can be plumbed into this framework. It's fairly easy. I played around with it simply. It's you can install it with Conda or pip, the usual methods. It's actually one of the default things in Anaconda, which is very popular in most scientific computing environments. It can function as a distributed executor. So you can go from just running it on a local laptop to running it on a whole cluster if you want. It actually has built-in support for Kubernetes, as well as Hadoop, Spark type resources. You can plumb it into a PBS batch queue you might have at an HPC center. All of these things. There's a lot of flexibility here with this tool. Another tool is Jupyter Notebooks. These, I'm guessing the majority of people have probably seen a Jupyter Notebook at some point, or at least heard the term. I know it's been in some of the talks we've had here before. But this, from a simple point of view, researchers use Jupyter Notebooks, in a web browser, like on their laptop sitting somewhere. And you can essentially, have a real interactive experience with your programming that you're doing. So let's, these boxes in gray here, that's just Python code. It's one of those things where you can put in some code, hit enter, and if you're generating a graph or doing something that goes out, it works, and then you get instant response right there in the same place you're doing your development. It's certainly a different environment than trying to write a program, compile it, submit it as a batch script, wait for it, your job to start, come back a day later, oops, it broke, start over again. Very, very interactive by comparison. In fact, you can probably think of it as really an integrated development environment, but it's also a integrated running environment, I guess. Certainly better than traditional things on a remote terminal. So the current model, as I said, we have batch computing. User submits a job, it goes, it runs places. In the case of CMS, you can submit to a global pools. Your job might go all over the planet. It comes back. Having to care about the storage is a very important component. A lot of times where your storage ends up or where your output ends up isn't where you want it. It's not where you are. It could be on a remote site, at which point then you have to copy it back. Maybe you can stream that back with like XRootD. A lot of times it's still, Grid FTP is still in use quite a bit. There's a lot of steps. And in the case of, you're doing something with visualizations, there's a lot of latency here, a lot of extra steps involved, none of which are, helping you get your research done faster. So maybe a new model for this is, picking that grand analysis challenge idea and finding a better way to do this. We could build analysis facilities, places where, researcher can go to get their computing and go get their work done. There's better tooling, as I said, like Dask is one of those. Better environment, Jupyter Hub or Jupyter Notebooks can give you a nice responsive environment. And if you combine those two, you can potentially have a distributed computing platform, so instant access to high performance computing, or at least a lot of cores, right there plumbed in with your web browser and whatever you're doing in Jupyter Hub. And that's kind of the general idea behind a lot of the analysis facilities that have cropped up. The one I'm talking about in particular here that we have at Nebraska is, we call it Coffea-Casa. One of the random logos that we have is over there on the right. Coffee, however you want to pronounce it, really stands for the columnar object framework for effective analysis. So it's essentially a, one of the new ways of looking at how to organize the data and make it apply in faster ways to computing, make things do better. So another view of this facility, this is right off of the documentation page or one of the various presentations the other people who do a lot of this and have made. So thank you for whoever I stole this from out of the team. Up here at the top, you can have the user's laptop, you've got your Python in your browser. This middle section here, you have Jupyter Hub and some Dask workers that get spawned up somewhere, any number, take your pick. You have all of this living in a Kubernetes cluster, perhaps, including caching. So you have access to the AAA Federation, which AAA stands for any data, anytime, anywhere. In physics, that's one of the ways by which you get access to all of the data that's been scattered around the planet. The big key point there is it's a way you can just stream data. So, researcher on their laptop, they might not have to have this huge data set sitting there on their laptop. They literally can just stream it from whatever computing center happens to be hosting that data. It's a really nice thing that's been built up. And that's where a lot of the data aspect comes from. On the left-hand side, there are a few words here: service X, skyhook, column service. There are a lot of things going on that I'm not even going to remotely get into that involve better organization of data and better ways of thinking about and organizing it, storing the output of it, maybe manipulating the data. I think it's Service X has a lot of support for transforming these root files into different ways that enable all of this other computing to actually happen and happen well. Yeah, and then over here on the right-hand side, we have an HT Condor pool. So one of the underlying ideas of this facility was, if we build this environment here in the middle that people have access to, we give them some cores maybe. We're doing this facility sometimes on the same infrastructure, or at least at the same data center or location, and with many of the same teams that are already support, like one of the tier 2s, Atlas tier 2 or CMS tier 2 in the US. There's a effort for this in Italy. I can't remember the institution it's at off the top of my head. But these places have, we have a huge amount of computing that already exists in the physics community. So maybe plumb that in there too. And that way we can scale out and utilize that. We'll see how that goes. So next question then is, what do we build this facility on? I'm a sysadmin by trade. I run cables a lot of times, and I actually enjoy that, being a rack monkey. So it's near and dear to my heart to care where this stuff lives and how it all fits together. Also from the Linux admin aspect. I think we have a goal in sight here then. We want to just build these tools and make them available to the users. And it's like, okay, great. And I said Kubernetes, and that's where the buzzwords come in. And certainly there are a lot of buzzwords. Here's one of the piles of buzzwords. And I say buzzwords maybe in a bad sense. I don't mean it in a derogatory way by any means. But there is just an immense amount of effort and tools and new applications and new ways of thinking that come up in this, our modern computing world, especially when you talk about cloud computing and that. This picture here in the middle is the current snapshot, at least as of yesterday, for the cloud native computing landscape. You can go to their website, cncf.io. They've got some pretty neat ways to, dig down through this data. They even have like a little trail, walk through your path and find what kind of tools you need for your given application. But this is the landscape of tools we have to pick from essentially when we're talking Kubernetes. Oops. This is also the place where you have things like microservices, talking about big scaling. I don't know if anybody's seen it. There used to be a wonderful webcomic making fun of all of the cloud and web scaling things. we use the term web scale, and sometimes it's a joke to say that, a thing is web scale or not. It doesn't matter as long as it uses these fancy tools, because then it's web scale, and you can't go wrong with that. And doing all this to make it, more resilient and agile in development. A lot of things to pick from. And in a sense, this is, just the huge playing field, the substrate which we can build things on top of. So a few of the ones that we actually do use, I pulled the logos out from here. There are some things here that are not logos from, cloud native projects, of course. Nebraska and Fermilab are not in that category. But to give you an idea of just, the number of things that exists that we had to use just to kind of get a simple Jupyter notebook going with, some computing that we had on the floor. This is just a, sub example or a few of them. So maybe to break it down into where those tools go, in a sense, Kubernetes, if you make an assumption, most people know what Kubernetes is or have heard of it at least. If it's not true, then Kubernetes is essentially, the way in which we are orchestrating containerized workflows. Google, you can go Google it yourself and lose lots of time seeing how many things out there are with Kubernetes. Just to run Kubernetes alone, like in-house, on-prem, and not, in Azure or in EC2 or someplace where they're doing this for you, you need a lot of things. Here we have there's a data store that keeps track of a lot of things. In our case, we're using Cryo as a container runtime. It could be Docker or Podman. The playing field moves very quickly. So whatever's here today, a year from now, there's probably going to be another new thing. And then there's a lot of effort that has to go into, kind of making this administratable from a human perspective. Without doing, a GitOps type workflow in Kubernetes and all of the YAML that's involved, I think you would go crazy. And even then, if you are doing a GitOps workflow, well, then, hey, now that's another component to all of this. The storage side, every computing thing needs storage. So in our case, we're using Rook, particularly Ceph. I didn't mention Ceph in this, but that's the thing that we're using. Authentication is a big component. There are quite a few authentication things out there in this ecosystem. Right now, we're kind of doing a simple thing where we're just using OAuth stuff, either via CI logon or using CERN's single sign-on. There's a whole stack of monitoring things, two really popular ways of doing monitoring and graphing, Prometheus, Grafana. Those are just a few of the components. And then networking too. Kubernetes itself out of the box doesn't really give you much in the way of networking, which is kind of an odd thing to say considering how large and powerful it is. But that's because there are probably dozens at this point of different container network things that you can add into Kubernetes to do various stuff. In our case, we're using a thing called Calico with Metal LB that lets us do load balancing. So you can make essentially an external presented load balanced service within Kubernetes. This is an interesting one because this is something you don't get out of the box if you're running bare metal Kubernetes and doing this all on your own. If you were in Google or Amazon doing this in the cloud provided environment, those are the types of things you get for free, which are really nice, which makes Kubernetes a lot easier. But in our case, we're doing this in-house. And then Trafix is another thing that we use, and we'll talk more about that in a minute here. I want to say, I guess Jason didn't mention at the beginning, but if anybody has any questions at any point, feel free to type them into the chat. I see, I have it here where I can kind of keep my eye on this. But if you have one and I miss it, just feel free to speak up. I'm happy to stop at any time. But for lack of a better place to put this one, and I'm not going in any order here of the things we're using, just to mention more a little bit on authentication. The high energy physics community X509 certificates are highly abused for pretty much everything. Still are. We're actually having conversations just yesterday about problems getting them supported in certain areas, and general frustration with them. But that's the state of things. There's been a push recently of course, recently could also mean like 8 years ago now. Time seems to fly. To move towards token-based auth, use tokens like side tokens. Derek is one of the people who would promote that as literally sitting feet from me outside my window. And that would kind of be a replacement for cert. So we're looking at supporting that type of stuff too. And then for most of the, yes, and Derek put a link to that in the chat if anybody's interested for side tokens. But for the most part, the auth that we have to care about, at least for this particular project, really kind of boils down to doing like OIDC or OAuth things. And like I said, we either use CI logon or CERN's SSO. So anybody who's affiliated with the CMS project should have a CERN account, and so we can rely on that. And then we throw TLS on most all of the communication that happens at any point of this, like even within Kubernetes. And so you get some minimal sane level of security and whatnot and with that. The next one I'll jump to is storage, and not in any particular order here. Storage is fun and evil at the same time, but certainly necessary no matter what. I mentioned with the new analysis frameworks and the challenge that there are some new types of storage coming out, or new ways of organizing storage, like ServiceX. I think I mentioned that you can transform data and do filtering of certain types on the fly. Object stores are starting to get used in certain cases, as opposed to just having plain old .root files sitting on a file system somewhere. There's a huge need for caching in all of this. CMS alone generates tons of data, and then there's Atlas and others. The movement of data around the planet is an ongoing challenge, and you need to certainly cache the physics data and make sure you have that available where your computing is or where your users are, especially if you want to go low latency. And then you also have to consider how to do that for the produced data. Where does that live? Does it stay in some place because it's going to help other people? All of these things are fun challenges to have to consider. In the case of an analysis facility, we also have user storage. Somebody's working on their laptop, they have their laptop storage, that's their persistent place. If we move that into a more cloud or ephemeral environment that they can be on their laptop and then they can go to their desktop in their office, they want the storage and the thing that they're interacting with to be the same. So we have to have storage for them too. So the question then is, where is this storage at? In our case, as I said, we were using Rook and Ceph. This is kind of how we get that. So Rook is a orchestrator with Kubernetes that lets you, make many different storage solutions to Kubernetes native ecosystem. If you throw enough YAML at the problem, so like this YAML here on the right is actually straight out of our currently running thing, with some stuff removed to make it fit the screen, you can end up with a Ceph cluster. If you've ever done Ceph, you'll notice things in here. There's the mon, you can have 3 monitors, might want 5 if you're going for more availability. There's manager, you can actually have the Ceph dashboard included, you can have SSL turned on for that by default. We'll actually have right now the monitoring is turned off, so we aren't getting fancy graphs in this case, but Rook takes care of a lot of this stuff and kind of mates what you would get out of the Ceph project to build a storage system and piles it into Kubernetes in a way that is honestly fairly easy to set up and administer and keep track of. This little bit over here on the right is actually, the naive way of doing storage on some nodes or hosts that we bought that have a bunch of NVMEs in them. Literally says, use all the devices on these hosts. Because they're NVMEs, you often want to have more Ceph OSDs per NVMe just because you gain performance that way with the queuing and whatnot. And so, yeah, we just say, here, Ceph, go, of these nodes, Kubernetes is running on these nodes, go make me a Ceph file system out of this. And it works, and it's quite nice. And it provides consumable storage for us. So we have storage now that we can use for the notebook pods, so the user pods, and they're persistent. User logs out, comes back, they can get their same little 10 gigabyte chunk of storage that we generate for them. We can also use this for our caching frameworks. We haven't done this yet. We have our X cache, so the CMS cache of data is running on decade-old hardware right now. But honestly, that's just because it works. It's in a container on that decade-old hardware. It can go into Kubernetes too. We just haven't done that. And then you can have storage for monitoring. Most Kubernetes instances, at least bare metal ones I know of, you throw Grafana and Prometheus, you actually have all that monitoring data is stored in Kubernetes itself and whatever storage you're doing. It's kind of a self-hosting thing in a sense. And it is just Ceph storage, so we can really use it for any random need that comes up.
So we have a question that came in.
We do.
When does it make sense to use a commercial auth system like Okta versus your SSO solutions? How does this computing center resolve across the rest of the Nebraska systems along with various enterprise system logins?
So the answer is probably that it almost always makes sense if you can afford it. Commercial systems, I know of Okta. I have no idea what the pricing scheme is off the top of my head, to be honest. So if there is a free tier, then by all means, feel free to correct me on that. With what I described, just using OAuth and any OAuth provider you can do. I mean, we could set this up so you could access it, with your Google credentials or Facebook probably. That works in the sense of, small test bed setups, or in particular, if we have the open data environment where the data itself that we're letting people access is meant to be publicly consumable, and you don't need to have more restrictions. I mentioned we have the CERN single sign-on. That one is somewhat important because there's an aspect of some of the data that it should only be accessible by people in the CMS project. I'm sure Atlas probably has the same thing, and I can't really comment to that, but it would make sense. And so using their single sign-on solution makes sense. This particular environment we set up, we have not actually plumbed it to our own university, our own Nebraska authentication systems. We haven't even plumbed it to our own Holland Computing Center, the research computing group identity management in any way yet, at least that I'm aware of. And so there's opportunities there. And I do think things like Okta and even just doing what we have, most of them support more than one provider. And so you can come up with whatever combination makes sense. If your university covers 90% of your needs, then it would make sense to do that with them. In our case, we just haven't done that because the people we are interacting with don't all fall into one administrative domain, really, and so we kept it open. Hopefully that answers that question. So another component here is Traefik. I'm guessing I'm pronouncing that right. I really don't know. Traefik is a very, very popular cloud native application proxy. So the thing that lets you steer traffic from one place to another. They have a commercialized enterprise version of this now. In fact, I think they've changed their logo since they made this cute little gopher dude, whatever he is. It's certainly popular, but they do have the Traefik proxy part. I believe is still a free open source thing that a lot of people use. And as you can see from this picture here, you're taking like URLs, for instance, from the web, maybe a domain, another domain with the subpath to it. That's the gopher, as Derek points out. So yes, it is, isn't it? That would make sense as it's written in Go and dressed up to be an air traffic controller, or whatever you call the ramp controllers, I guess. And then you take that and you can steer it to different things. And being Kubernetes native, you get to steer to things that you talk about in Kubernetes. So if you have a deployment that has a set of pods, running a load balanced web server or the identical copies of that, you can have Traefik know that and point your traffic to the right place. You can also use Traefik to do not just HTTPS. You can do arbitrary TCP, which is actually useful. We do that. That's Dask communicates via TCP, and so Traefik is actually the method by which we can steer or expose Dask workers to other places. And there's, of course, you can see the little lock here, HTTPS. There's a whole slew of TLS and other support within Trafic in order to keep things sane and not too crazy. So I mentioned a few tools so far, so maybe I should take another step back out of this hole that I dug myself. This is kind of a picture of what this looks like from a user perspective. So, this is not an Italian in a coffee shop, it's a monkey with a laptop, but they go to a web page, and these are the two URLs up here at the top, if you can see them. I will say that Coffea-Casa, that is the CMS only one, so unless you actually have CERN credentials, you're not going to get far with that. The open data one is in theory available for anyone, with the caveat that there is a manual step when you do your CI logon with that you will have to be approved for. So unless you seriously do want to look at this or play around with this, I wouldn't bother trying. There's one person who would probably hate having a bunch of requests come in within the Open Science Grid that has to deal with that. But if you are interested, maybe shoot me an email. Address was at the beginning of the talk on the first slide, and I can put it at the end too. And would be happy to let you spin these things up and actually play with it if you're interested. But what it looks like, user goes to the page, they authenticate with CERN single sign-on in this case. You get to a Jupyter Hub web page. You can see my email address at CERN in this case there. Feel free to use that email address, I guess. It's another valid one. And in our case, we have only one Coffee notebook image that we are kind of have exposed right now. But you click start and it grinds through and it gives you a Jupyter notebook. And this gives you a nice little progression bar of what's going on. So maybe to add to the understanding of what all this is doing, here is another view of this. So as I said, user browser, you're actually hitting Trafic pods that's steering traffic to a Jupyter Hub instance running in a container, on Kubernetes. You go through the authentication steps, you get a new user environment spawned. These bolded parts here and these log entries are kind of what actually happens. I successfully got assigned a environment, so to speak, on a physical node somewhere. This is in our data center under the stadium. We got some storage container started. We got a notebook container started, and we had a Dask worker container started. And so we get all of these little things that are within Kubernetes built up as containers, and that is my environment that I get to play with. Stolen again out of our documents that somebody else wrote. This is kind of that picture I showed before, just with a little more colors. The green stuff on the left, that's the pods that get made when you click start, something fires up. So this is like my own little playground here. It's a per user thing. This bit on the right is the magic that happens if we want to scale out and have the Dask. It's kind of a guaranteed Dask and Jupyter notebook environment for a user. Scale out to Dask workers that get spawned up on like our tier 2 cluster, so a traditional high throughput HT Condor cluster. They can talk back and forth, and you can gain resources that way. And then, as I said before, too, the data access for the large part is via the AAA Federation and using Xcache, which is X-D, which is kind of just become the predominant way the data moves around. So where do these pods live? I said we spawned up, we clicked the start button, we got some pods, containers running on a server. Where are they? They are not on these computers, because these computers are obviously spilled out across the loading dock. This wasn't me that caused this, by the way. We did do this originally as a prototype on old hardware, not this hardware, but equally old and sad hardware. First iteration was kind of some old Dell R710s. We threw some SSDs in after we were convinced it would work. And we had a bunch of Sunfire nodes that were the compute. And yes, Sun, like the Sun that was a company that made computers back in the day. That is how old this hardware was, but it worked. In fact, it worked well enough that we had money to build a better prototype, which I guess would actually be, the production instance, so to speak. And so this is a picture of the new stuff we have, the better, brighter Blinky lights, because they're new Dell servers and they have the ridiculously bright blue lights on them. This funding came kind of from the CMS projects as well as IRIS-HEP. IRIS-HEP is a NSF grant doing, oh gosh, I can't remember. It's working in the software space for high energy physics. I forgot the acronym already. Derek's rolling his eyes at me, I'm sure. But the hosts here are fairly nice. They're fairly beefy hosts. If you're keeping score, 12 of these hosts with these CPUs are roughly 672 cores, 1344 threads. So not a sad chunk of CPU. We do triplicate replicated SEP. So this is really, at the end of the day, about 100 terabytes of usable, purely NVMe storage. And all of these nodes have 2 by 100 gig network connections to them, to a pair of Dell switches at the top of the racks. You can see the big chunk of cables over here. That's what those are. Similar facilities that were built up elsewhere have, they've invested some hardware money to kind of build a better environment to live on. This just happens to be ours. And as you can imagine, by the build here and just what we're building, all the storage lives here, the compute lives here. So, somebody spinning up a Jupyter notebook, you can play in this one rack here in this, modern hardware, nicely coupled environment. And so one would hope things go faster and it's a much more friendly, interactive experience when you're literally only dealing within one facility in a rack. So I want to switch to the funner part, in my opinion. This is moving back out of my hole into the network layer, because like I said, I like plumbing these things together, and that's I wired up that rack you just saw, and so I like to know how the bits are flowing around. So Kubernetes, as I mentioned, has a lot of networking options. The network interfaces, I've lost track of how many there are. We use Calico for the container network interface. I think it's called Project Calico, actually, and they are also have a commercial kind of arm forming around the company, but you can still get away with just straight Calico stuff for free. And we started using it in BGP mode. With the original prototype, we did layer 2 on our existing CMS tier 2 network, so to speak. But for this new rebuild with new hardware, we did BGP, and so it's more different, but in my opinion, more fun and more scalable. And I'll talk about it here in a second. And again, metal LB for the load balancer, because you don't get that out of the box with Kubernetes. And it wasn't until recently, the last year or two, that Calico in BGP mode and metal LB really all worked together exactly as you would want to make a on-prem solution or a raw bare metal solution work. So if you had looked at this in the past and you found that it didn't work because, well, they didn't play nicely together, they thankfully do now. So it's gotten a lot easier. Again, provided you throw enough YAML at the problem. So just to give you another idea of how this connects to the rest of the world, here we have our campus WAN. So you people out there in the internet, directly to our we call it a router. It's a Dell switch. That's our router for this particular data center. It connects a couple hundred or 100 gig links to this pair of nicer Dell switches, the 64 port 100 gig ones. And then we have 400 gig, 100 gig connections to this pair of top of rack switches, the ones that are in this picture over here. And that's just ECMP, balancing there. So nothing really fancy as far as until you get down to this layer. So within this rack is where all this Kubernetes magic happens. And so I said, as with most Kubernetes stuff, you throw enough YAML at a problem and you make stuff happen, and pods spin up and run around and do things. This is what the Calico configs look like, or at least a chunk of them. Not very exciting unless you're doing this, I suppose. We have some things that you expect to see in BGP over here. By the way, never let your brain convince yourself that BGP is port 178. I did that for like 3 days. I don't know why I was convinced that BGP had always been port 178. And so, yeah, I lost like 3 days of my life to that one. That's what I get for not looking at Etsy services, I guess. And you can see over here, we have some service cluster IPs, so like internal Kubernetes IPs that it gets to build, when it's making pods on different hosts, as well as our external ones. We just have a /24 that's our external facing on this. This here, oops, okay, I forget, can't highlight that. This here is actually one of the hosts. So one of these, servers, Calico CTL can show you the peers. So each of these servers has Calico containers running on it in Kubernetes, and it pairs with each of these top of rack switches. These are really in a VLT pair, but we pair to each of them individually, just because that's how it's currently set up and how it happens to work. There's some legacy, buggy, half technical reasons for that with the Dell implementation. So, what does it look like from a switch then? We have pods that are running on a host, containers running on a host. That host pairs with top rack switches. Calico is advertising the IPs of these pods to, the switches via BGP. So up here on the right, this is, actually the routing table on one of those switches. We have a couple of default routes that go up to the rest of our network. As I said, here's a bunch you can see here that are from the first three hosts in that rack. These are the hosts going up. This is an error. I tried to correct this because one of the host numbers was wrong, and clearly I fat fingered that. So no, this is not 2 route entries for the same host. It's supposed to be a 9. And then we have these other entries here. These are actually public facing ones that are from a pod. So I spun up a load balanced, or a Kubernetes load balancer that goes to a set of 3 pods that run on 3 separate hosts. All they are simple web servers that just spit back something. If you want to, test my luck, I guess, or test your luck, you are welcome to try to just hit this address or this IP address and see. You could hit refresh a few times, and in theory, you'll cycle through 3 slightly different responses from those pods. Calico actually advertised those pod addresses out to the world, or at least to our switching infrastructure. It gets aggregated before it leaves our world, of course. But it's kind of neat, I think, that you could have, any of these tools, our Jupyter Hub instance, notebook, whatever, spin up, you have a pod, and you're advertising the address of that pod automatically out to your network. It makes it surprisingly simple once you have all the plumbing in place. And to answer Timothy, right now, all of these Dell switches are actually still running Dell OS 10. I have not had time to look at possibly switching this to Sonic. I don't even know if Sonic has a full BGP implementation yet or not, or if some other things might be better. But in our case, all of the Dell switches are all Dell's OS 10.
We had one more question come in. It was just to me directly, so you probably didn't see it. Do you use the Kubernetes cluster for anything else apart from Jupyter and Dask?
Well, yes and no, but not yet on the new stuff. But certainly that is a longer term goal. So we have low hanging fruit like Squid caches, or Squid proxies, not caches. For instance, that, they're really trivial to containerize. We run those on dedicated hardware for our physics tier 2 cluster that literally sits right next to all of these racks and is connected to the same core switches. We're looking seriously at moving some of those things into this same Kubernetes cluster that runs all the analysis facility stuff. At some point, spinning up worker nodes for the traditional cluster within Kubernetes makes sense, I think. And moving as much of our support that direction. We have a big overlap of effort within our shop of a lot of people doing kind of different things with Kubernetes in different ways. And as much as it adds complexity, which I'll touch on here in a second towards the end, I think it is worth it. And so, yeah, I think we will end up putting more there. The only reason we don't right now is that we don't want to break the currently functioning analysis facility as we figure out how to do all of this, but soon. I guess one last thing, as I said here too, you can put whatever you want and have it advertised out to the network. Calico itself actually provides a really robust set of network policies, so you can do kind of all of your policy framework on who gets access to what applications or what pods are allowed to talk to what other pods. All of that stuff is, within Calico, and you can automate, do whatever you need there. And since you're just doing BGP now to your network, you can treat it as normal traffic and do whatever else you might want to. So I guess I said I was going to talk more about Kubernetes here in the future, and yes, it was the next slide. So, a lot of the internet says Kubernetes is easy. And in many cases, it really is. If you Google any bit of this, you'll find plenty of blog posts of, type these 5 commands and ta-da, you've got, a magically spun up multi-tier web application with databases and all of this. That's one view of it, of course, especially if you're a developer. It seems really easy and trivial to do all of this. But sometimes I think people forget the complex plumbing that has to exist underneath this. If you work in a cloud environment, Azure, EC2, whatever, a lot of that plumbing is taken care of for you. You don't have to see it or care about it. When you work in academia and nobody gives you a credit card or a P card to go out and spend dollars on building infrastructure in Amazon, then you do it in-house, and you have to do a lot of the things the hard way, and then also be responsible for all the traditional bits and pieces like monitoring, the logging, the plumbing, building up frameworks to do that. And yes, as Timothy just typed, it still is a cluster, and all of that, that entails being a cluster. And so we're still kind of learning, I think there, just how to balance admin time, people FTE time with the complexity that goes along with having, another layer of stuff. I think we're getting better at the extra stuff from Kubernetes. Once you get good at it, then maybe you can start making the other, things of maintaining OSs and that stuff underneath somewhat simpler, kind of trade-off. Still much to learn there and experience to gain. I don't think it's, for everyone. I mentioned tier 3s at the start of this. People who have, limited computing staff to make their science go with their institution, don't try to just jump in and do Kubernetes. But that said, there are plenty of opportunities for this to, be built up and made in a way that can be consumed by others. There's a lot of Kubernetes out there right now. There's Pacific Research Platform, huge investments from Open Science Grid. Everybody's containers, everybody's Kubernetes. That's where most of the signs and fingers are pointing, I guess. So I think there's a lot of potential coming here for that to happen. One thing too that I think is lacking is security focus. Like I said, it's really easy to build this stuff up. Well, not easy to build it. It's easy to build it once. We ourselves have made the mistake of, building a prototype and then forgetting how we built the prototype, and now we built the production thing and are having to relearn how that works. So it can be complex. But that said, I think it was successful. So again, you can do things the hard way, or you can build with all of these tools that you can pull out of, those diagrams full of icons. We did that. The stuff that we built, I think, is reproducible. Like I said, there are other projects out there. I guess I didn't even know if I finished this slide. Slate is a effort that's doing a lot with containerization of many pieces that high energy physics uses, like caches and whatnot. There are a lot of other analysis facilities currently being looked at. There's one at Fermi. I really apologize, I can't remember the one in Italy. And from a 10,000 foot view, all of these things, I hope we're going to start to come together, and maybe that'll be the new way of doing computing in this area. So I think it was successful. If you want, you can click that link at the end there. This is the end of my slides, by the way. That's the documentation we have for this particular project and this particular analysis framework. You're welcome to look around the diagrams if you wanted to see something else in detail. And with that, I will happily take any questions if anybody has any other ones.
All right, first question, from a networking perspective, what did you find most counterintuitive about Kubernetes?
Ooh, that's a good question. Most counterintuitive. I don't know if I would necessarily say counterintuitive. Well, I guess maybe from first glance it probably was. The sheer complexity of of it seemed, daunting at first. I've honestly not experienced much in the way of the other network interfaces that people have used. There's Cilium, there's a lot of other popular ones, especially even in high profile large sites with CERN. I've stuck and lived and breathed Calico only, really. Once I got my head wrapped around what Kubernetes was doing or wanting to do with enabling pods and containers to talk to one another, it got easier. Still daunting and complex at times, but I think the biggest thing is, unless you fully understand why the networking is being plumbed the way it is, it just doesn't necessarily make sense at all. And at the same time, it's not easily viewable or consumable in from a human standpoint. Look at IP tables. In our case, we use IP tables still, and Calico makes a whole boatload of rules, and trying to actually go through by hand and piece together how packets get from one place to another. It's doable. I've done it. It's not fun. And yes, yeah, Timothy in the chat mentioned for him it was the doing the magic for services. So yeah, the concept of load balance services or external services, and just wrapping the head around that, and how you're presenting an address that's essentially in a way getting proxied to other ports on other possible hosts, or in some cases ports that are getting proxied to every possible host, depending on which service type you're talking about. Is kind of really crazy to wrap your head around.
And the next question is, are there any plans to support other programming languages like R, or support for other tools like MATLAB?
So that is a great question. Within this particular project, and we have limited time, and so putting more effort into this, the Coffea-Casa project, to support other things that aren't what the physicists need, doesn't make sense. This idea of building an analysis facility, and it doesn't have to be Kubernetes, but right now I would say, yeah, it's probably the right tool for the job. But building an analysis facility to support science in general, yes, I think definitely should support things like R or other tools. We run an HPC center. We have a few clusters here at Nebraska as well. We provide open on-demand, which kind of right now is the most user-friendly, in a web browser interface to a cluster. And in that, they get to use things like R and MATLAB, and the support is there. Certainly, being as you can make those appear, in a web format, or at least in a user accessible format, it certainly is doable in this type of facility. There's a effort within PRP, I believe, to go all the way, or at least somebody who was doing testing, where you go all the way to, essentially providing remote KVM access to containers that get spun up. So, a user gets their own little environment with all the stuff that's going to support their science, and, they get X11 forwarding essentially to that environment. And so, your user has now whatever visual thing you need, maybe even 3D rendering from GPU output, and they get to, interact with that environment. But that environment could be within a Kubernetes cluster that's, built up as an analysis framework, like what I just talked about.
All right, I think we may be out of questions. So thanks again for giving this overview. I learned a lot, and I learned that there's a lot of tools that I've never even heard of before. So
yeah, look at the cloud native thing. There's more than I knew existed too.
So thanks again for going through everything. Send me the slides when you get a chance. I'll make sure those get posted. And for everybody else, we have a 1-week break, and we'll be back on the 15th talking about another P4 topic, dynamic router buffer sizing using passive measurements and P4 switches from the people at University of South Carolina. So we'll talk to everybody in 2 weeks. Thanks, and have a good weekend.